A warm greetings to one and all here. Myself Dr. A. Mydeen Bibi, Assistant Professor of Mathematics, the Standard 5X Rajaratnam College for Women. We are all together to learn something about random variables. I hope you are all going to enjoy the session. Some learning objectives of the session. To find the values of the random variables in an experiment, to classify variable as discrete and continuous random variable, to construct the probability distribution of a discrete and continuous random variable. Random variable is an even space. We are going to find 0 or 1 as a value in the sample space given. The definition of a random variable. Let S be a sample space associated with the random experiment, a function x from S to R which assigns to an each element omega belongs to S. One and only one real number is called the random variable. Thus x of omega represents a real number. So when we have an event of an outcome, we will find 0 or 1 as a single real number as a variable. The sample of the space of a random variable x is defined to be the set x omega such that omega belongs to S. I am giving some mapping here. The mapping shows how the random variable x transforms the sample space S into a real number space zeta with the point omega in a subset A mapping to x omega in subset C. So I am defining the random variable, that is the process of assigning a value to each event in the sample. Let me define the random variable with a simple example first. When we tossing a 2 coins, what will we get? One head or tail. Consider a tossing 2 coins with a sample space S, that is 2 heads or 1 tail, 1 head, or 1 head, 1 tail, otherwise it is both of them are tail. We assign uniform probability 1 by 4 to each element, define random variable x as the number of heads in each outcome. I am mapping the random variable here. My task is the number of heads in each outcome. The probability that the 2 heads is, I am getting, when we toss the 2 coins, I am getting 2 heads. So the random variable is 2. When I am getting only 1 head, I am getting 1. When we getting both of them are both the coins getting tail, I am getting 0. So the sample space of the random variable x is 0, 1, 2. I am defining the probability of 0, 1, 2 here. That is the probability of 2 tails, that is the favorable outcome divided by the total outcome. The total outcome is 4. I am getting only 1 head. I am getting only 1 head is 1 by 4. I am getting 2 heads are 1 by 4, I am getting 2 tails are 1 by 4. Here I am going to explain one more example, that is a deck of a card, drawing from a deck of a cards. We all know about there will be a 52 cards in each of the deck of the cards. I am defining the sample space as a standard deck of 52 cards with uniform probability 1 by 52 for each outcome omega. I am defining random variable here, that is x of omega. When I am getting 4, if the card is an ace. When I get 3, if the card is a king. When I getting 2, if the card is a queen. When I getting 1, if the card is a jack. 0 otherwise. The sample space of x, random variable x are 0, 1, 2, 3 and 4. I am defining the random variable mapping here. The induced probabilities demonstrate how the random variable transforms card probabilities into numerical probabilities. I am getting the probability 0, that is not ace, king, queen or jack, that is 36 by 52, that is favorable outcome divided by the total outcome. There is a 52 cards in a deck, therefore the total outcome is 52. When I am getting only 1 jack, that is P of 1, that is 4 by 52, like that, getting queen, getting king, getting S, these are all the probabilities of the drawing from a deck of a cards. Distribution function, one of the important main role participating in random variable. For a random variable x, the function f from R to R defined by f of x, p of x is less than or equal to x, where minus infinity to infinity values, that is for all real numbers x, is called the distribution function. So that is the real number 0 to 1. When we get the outcome, that is 1. When we are not getting the outcome, that is 0. If A less than B, then P of A less than X less than or equal to B, that is f of B minus f of A. This follows because the events are disjoint with the unions, that is A and B are the unions of the session. Next, I am going to take the types of random variables. Here we are going to learn about two types of random variables. One is discrete and another one is continuous. First, I am going to define discrete random variable. So, discrete is a countable, continuous is a uncountable. Yes, a random variable X is said to be discrete if it takes the at most countable number of values x1, x2 and so on xn. Let P of X is equal to Xi, which is equal to Pi, then by the definition of probability summation Pi equal to 1 when we get the outcome. If I am not getting the outcome, I am getting summation Pi 0. For any subset A of a range space, that is a sample space, summation Pi Xi belongs to the A. When we define the discrete random variable, we must know about the probability mass function. In the sample space, for a discrete random variable X, x1, x2 and so on xm, let P of X is equal to Xi is defined by Pi, then F is called the probability mass function. In the discrete random variable, the distribution function also defined as a step function. That is the distribution function f from R to R is defined by f of X. X is less than or equal to X, that is summation Pi. This summation also finds the value from 1. So for a discrete random variable, f of X is a step function with the jumps at each point X, and the size of the jump at Xi is Pi, which is probability of Xi equal to Xi. One small example for the discrete random variable, which one is a countable discrete random variable. Consider 3 independent tosses of a fair coin with the sample space. I am giving the distribution function to as an image also. I am also defining the probability. When we toss as 3 coins, there is a possibilities that 3 heads, 2 heads or 2 tails or 3 of them both are tails. A uniform probability of 1 by 8 is assigned to each outcome. Each outcome will be get the probability as 1 by 8. The random variable X counts the number of heads only. I am going to find the probability as a random variable counts the number of heads. So P of 0, when I am getting all the turns are tail, there is a probability 0, I am getting 1 by 8 as assigned. Like that, when I am getting 3 of them as a head, P of 3, that is the probability of P of 3, that is 1 by 8. Other also I am defining here. I am defining the distribution function for the 3 of the coins tossing. So f of X I am defining. So 0 to 1, summation Pi will be equal to 1. So 0 as when X is less than 0, when X is greater than or equal to 3, I am getting 1. Otherwise the probability is equate to the 1 by 8, 1 by 2 and 7 by 8. Like that, I am going to define the next type of random variable, that is continuous random variable. This is uncountable. There is a lot of examples for the continuous random variables. A random variable X is continuous if it take any value in an interval, that is uncountable intervals. This concept applies to variables like heights, weights and temperature that vary continuously. The probability density function also defined in continuous random variable. It satisfies 3 of the conditions, that f of X is integrable over minus infinity to infinity. F of X is greater than or equal to 0, there is a non-negative value. Integral of f of X must be equal to 1, like the probability mass function summation Pi which is equal to 1, like the integral of minus infinity to infinity f of X dx is equal to 1. I am giving the distribution function and probability calculation also given as a hint. The key properties of a distribution function, we all must notice that these 4 conditions must be satisfied for the random variables as a discrete or continuous. F of infinity equal to 1 and f of minus infinity equal to 0. F of A, P, probability of A less than or equal to X less than or equal to B, that is f of B minus f of A as a probability function, calculating the probability function. F of X is definitely it is an increasing function. For a continuous variable, we must calculate f probability of A less than or equal to X less than or equal to B as A is less than X less than B, or else A less than or equal to X less than B, or else A less than X less than or equal to B. We must notice that Unlike discrete random variables, where single points have positive probability, continuous random variables assign the zero probability to individual points. Probability is only meaningful over the intervals. I am giving a comparison of an example. First one is a discrete distribution, second one is an infinite series. These problems demonstrate the practical application of probability function for both finite and infinite discrete random variables, that is countable for discrete and uncountable for conditional random variables. The first uses the binomial distribution structure, while the second involves an infinite geometric series. Both illustrate how the fundamental principles summation pi equal to 1 ensures a valid probability distribution. I hope you all enjoyed the session. Thank you so much.